So my name is Christopher Lee, and I'm going to be talking about the early detection part of dealing with water problems. So the furthest away from the plant, dealing with the actual problem in the surface water. So a little bit of background on our company. So we were founded in 2018 to address specifically the growing problem of HABs and especially the monitoring side of it. Previously, the founders were involved in companies that grow algae on purpose for biofuels and for nutritional products, creating an optimization and sensor package and software package for those growers. Going on to Aqua Real Time and the product called the Algae Tracker. We had a first prototype in 2019. During COVID, we were doing lots of pilots in the United States, and we've grown to about 120 deployments this year, up to 2 years at a time. We were originally funded by Environmental Protection Agency, as well as private investors. So we have world-class optoelectronics engineers, best-in-class mechanical and electrical engineers. We have at this point about 35 customers involved in the product. So why is the early detection so important? Well, I think as you guys all know, there's a very quick growth phase for algae, and it can happen in just a few days. It can also happen in just a few hours based on currents and wind directions. So if you can have something at the source water that's easily deployable to a lot of locations and easily installed and maintained, then you can get that early detection. When you combine that with analysis with, for example, the flow cam, as Polly is going to be talking about, you can get a really good picture of what's going on, and then that will enable the preventive measures. So you can then dramatically reduce your operational expenses, your downtime in water plants and closures. So you get this process flow of initially the detection back into treatment with various methods, such as Dave will be talking about or has talked about, then back into a validation stability phase where everything is looking good, and then anything happens again, boom, you're back into detect, treat, and the cycle continues. So previously, these are previous monitoring methods, previous sensors. Typically, there would be a need for these individual probes that would be assembled into bigger sondes, and then those sondes would have to be assembled into third-party buoys, such as what you might see here. This would end up weighing in the 50 to even 100 kilogram weight range. It would take 2 or 3 people, 2 or 3 days to install. Little cranes would be required to move these objects. But you could get a lot of different measurements, including the chlorophyll and the phycocyanin, which are the green algae and blue-green algae. Costs were typically in the $30,000 plus range. So what we wanted to develop is something that is plug and play, very easy to use, lightweight, easy to install, easy to no assembly required. So we developed the Algae Tracker, which you can see here on the left. So this is an IoT sensor buoy. You just take it out of the box, pre-assembled, place it in the water, clip it to an existing fixture. That could be a navigation buoy. It could be an anchor that you place, and just press the power button, and it will automatically start taking measurements every 30 minutes and publishing those to a web dashboard, cloud-based, every 2 hours. So specifically what we're measuring is chlorophyll, phycocyanin, and turbidity. So that's the green algae proxy, the cyanobacteria proxy, and turbidity, good catch-all for a lot of different things. Water temperature, solar light, and we also have the GPS on board. Using that GPS, we pull in 4 more parameters for a total of 10 parameters, which are the wind direction and speed, the precipitation, and the air temperature. So this gets published every 2 hours to a dashboard. You can see here, there's the first page would actually be a map of all the different devices that you own. Then there would be color-coded gauges, green, yellow, red, depending on the severity of the issue, and you can get alerts set up for action thresholds when someone needs to get out there. Of course, historical charts. We have first ever deployed analytics for correction factors on a lot of these different fluorescence-based sensors to make the accuracy even better. A little bit more detail on the device itself. It's 4 kilograms, 35 centimeters in diameter, has its own solar panel, of course, so it's autonomous on a power level, battery inside, so even without light, this will go for a full month without any kind of intervention. It has its own anti-biofouling system on it, which is very effective. You can see this device, for example, has a lot of biofouling attached to it, but the window will stay completely clear. And it can get a lot worse than this, much, much worse, and the window will still stay clear. So the idea with these is typically you deploy them in a defensive perimeter around assets. That could be a water intake, it could be beaches if it's a recreational area, etc. Real quick, here's some accuracy data from a third-party independent lab showing the results for both the blue-green algae here on the right and the regular algae on the left. So the x-axis is the true concentration of that parameter, of the analyte, of the algae, and the y-axis is our measurement. So a perfect sensor would be a perfectly straight line with an r-squared value of 1.0, and so we're up at 0.99, so it's a very accurate sensor. You'll get a degradation of this accuracy in the field. This is in a lab setting. However, you'll still get a very good indication of what's going on as a trend. And there's a high a high similarity in the behavior from one sensor to the next. So this is what a typical recreational area, and which is going to look fairly similar to how you would deploy for drinking water, such as you would have out there. Basically, you attach the tracker. Typically, at this point, we're using stainless steel cable, not rope. This is a very a gentle waterway here, so it's okay, and there's no theft. But you would attach this to a secondary counter buoy, and then that would go down to an anchor. So in this case, we have this team of lake management company, and the goal here, this is Orange County in Los Angeles, California. So the goal here is to prevent these big blooms that occur that make animals sick, humans sick, and it forced the closure of this public park that that causes a lot of bad press, so on. Here's a quick look at how the dashboard looks like. You have, of course, the time the device was last online and posted, which is typically every 2 hours, with the measurements being every 30 minutes. Signal strength here, this is a cellular platform. Battery status, of course, will usually be around 80%. A map of all of your devices here and also on the previous page. The location, weather, of course, these color-coded gauges, which, as I said, you can set them for alerts. Historical charts with different kinds of analytics that you can apply to correction factors. For example, for something called non-photochemical quenching. I won't go into that, but I can certainly discuss it later. And then we have a lot of self-diagnostics. We can tell if something is going on in your device. We can notify the people, and it becomes very easy to keep these running all the time. So I'll go through a couple of quick case studies. This is an example where treatments were done. This is a 2-week time frame. The 3 pink bars here are the treatments done with algicides, and you can see the blue and the green are the chlorophyll A and hypocyan response. To put it in perspective, the chlorophyll started up around 1600 RFU, which is about 160 micrograms per liter. That's about 7 times a rule of thumb for swimming limit. With these 3 treatments, they were able to bring it down to about 25 micrograms per liter. And so this was a very successful treatment. It was documented by the software. This data can be shared around to different stakeholders so that they can find out how their water is doing at all times. Another example here, this is in Massachusetts, close to Boston. There was a turbidity event where you can see a couple of spikes here in the turbidity, and this was captured long before it was seen in the field by the tracker, and it turns out it was a sediment flow event. You can see here the sediment flow in this picture in Lake Quinsigamond, and the tracker was placed out here somewhere. This is a drinking water utility for Los Angeles. So they are using our devices in several locations. This is a remote location where it's very difficult for them to get out there and take measurements. It takes them pretty much the whole day to drive out, take measurements, and come back. So they only do it once a month. Before they had the tracker, now they're doing it, it's a constant data, every half-hour resolution. You can see the unit is here. And here on the right, you can see the red dots. The red dots are samples that they took themselves, and the green data is from our sensor. So good correlation here between the two. And specifically, the correlation between the two data sets was of about 0.83, which is very high for environmental data, given that you can't have the exact same time frame. The water's moving, it's flowing, and so on. Was there a question there? This is another example in a very eutrophic lake in Utah. It's Utah Lake. You can see even just from the color here, this enclosed marina. The two trackers were placed here, and this is just an incredibly, almost a give it up type of lake, and as far as how much eutrophic activity there is. So they've had lake management companies do treatments in this particular area, and so the trackers were to document that. So real quick here, you can see algaecide treatments on 2 time frames with these gray bars. The green line is the response of the tracker sensor, and the dots are from YSI probes that we used. So after these treatments, there was very rapid decline, but because this is such a eutrophic location, within a few days, you would go straight back up. And then after the next treatment, it would fall down again and then go straight back up. So this was not a successful treatment, but it certainly showed the potential of these trackers to document what's going on. So I'm going to stop there. And thanks so much for listening, everybody.